Okay, so hello everyone. Welcome back to our Toronto AI Robotics Ayal seminar. Today is the first seminar of this semester, and we are glad to have Ayal Taitler to give a talk on stochastic planning and reinforcement learning. Ayal is a postdoc fellow at the University of Toronto, working with Professor Scott Stanner. His research interests lie at the intersection of reinforcement learning, automatic planning, and control theory for decision-making. Ayal received his PhD from the Technion working on hybrid planning under the joint supervision of Professor Aris Karpas and Professor Per-Olof Gertman. Before that, he received his Master of Science in Reinforcement Learning for Robotic Air Hockey under the supervision of Professor Nahum Shinking, and a Bachelor of Science both from the ECE faculty of the Technion. He has over 10 years of industry experience in software engineering and AI research, and was a lecturer at the ECE faculty at the Technion. So yeah, Ayal, we're all looking forward to your talk. Please feel free to take over.
All right, thank you for the introduction, and I'm super excited to be here today and very honored to be the opening speaker. Let me just share my screen. Okay, so I hope everybody see that. Okay, so I'm going to talk about stochastic planning and reinforcement learning, and I'm basically going to talk about our vision and what we're doing here in Toronto in my postdoc. And it's a very natural continuation of what I did before that. So what happens in the middle, it's what interests me the most. It's the connection between disciplines, how to merge approaches. I did that also in my PhD and my master's. And I think that the most interesting things can grow when you try to combine things together. So why should we even want to do that? What should be the motivation? So there are a lot of hard problems out there that we still don't fully understand and know how to solve completely. So we can have hybrid spaces, we can have continuous problems, and we can have discrete or Boolean problems, but problems that have both continuous and discrete properties are very hard to solve, both for planning, control, and for pure reinforcement learning. Noises, exogenous noises operating on the states, on the actions. This is also something not completely understood. And states of interest, like if you have the state space and you have only a subset of the states that you actually care about, this is only a subset is related to the decision making. How do we identify it? How we know how to ignore the rest of it? So there are a lot of interesting questions about these areas, and just using one discipline and one set of tools is, I think it's like hard. It will be easier to and more elegant to combine things together. So we all know this scheme, this paradigm of think, plan, interact, and what interests us is the think and what it means by think. It's learning, planning, what is it? So we can solve this problem by programming by hand, like telling exactly the agent what to do. We can use learning. It can observe what happens in the world. It learns what to do, but it doesn't really know beforehand what's going on. It doesn't know that the basic interaction, it doesn't know the model. And we can use model-based planning, which can know the model, can do a lot of interesting things, but it does not evolve over time and cannot learn things that you did not specify in the model explicitly. So everybody knows that it's part of the background. So learning has a lot of potential. We see that every day. Now we also see this huge jump in large language models. Machine learning has a lot of potential. But when you learn one task, when you take that algorithm, that agent that learned this one task and put it on another, the transfer capabilities and the understanding of what's going on, it's, well, we will not do that, obviously. So I will say a word about automated planning. So in planning, what we want to do is to devise a general solver. So I will give you an algorithm, I will give you a box, and you will give me whatever problem you want to solve, and it will find a solution. It does not learn. It uses usually a lot of tools that developed in the AI community. And as long as you give it in a agreed upon format, you can basically solve everything. It might take it a long time. It might be very hard to solve, but in theory, we want to find a general solver that can solve every problem that you can put in this format. Okay, so both approaches has the obvious advantages and disadvantages. And in this talk, I'm going to focus mainly on MDPs. This is the problem of our interest. MDPs, not general planning or something like that, specifically MDPs. So everybody knows the problem. We have states, action, rewards, and transition models. And everybody knows a paper that starts with the MDP of the problem defined by the tuple SART, but what is, or what are SART? How do they look like? So we need some way to show them so everybody can understand. So if I'm giving you a model, you can use it in your algorithm and not specifically in my algorithm. So we need a language, a unified way to describe these problems. So languages, we have a lot of languages for planning and learning problems. We have scripts. I guess everybody's a little aware of scripts at least. It's basically a propositional language. We have actions, initial state, goals. We have add and delete effects. We're adding propositions, we're deleting them. This is a basic of, I think, the language in the AI community. We have PDDL, that's for deterministic problems usually. It's very similar to scripts, but it's lifted. So you don't need to specify directly when you describe the problem. You don't need to specify everything. You can specify these operator templates and then just instantiate them. And you have PDDL, which is a non-deterministic variant of PDDL. You can have like these stochastic effects of the actions. It's still, you cannot describe every MDP with that, but it's a one step further. And earlier competition in the international planning competitions in ICAPS were using PDDL. It's a very interesting language, but it's still somewhat limited. And I'm going to focus on RDDL, Riddle, as we call it. It was written by Scott Sanger, the professor I'm working with. It's fully lifted, it's fully stochastic, concurrent, factored. So when you describe a problem with Riddle, you have a lot of information on the problem, and it's very compact and efficient. So it's very easy to work with, to describe problem, and it gives you a lot of room to do analysis that you cannot do without it, or at least it gives you the tool to do this analysis that you can think about before. I'll start with an example of why are these problems interesting and the differences between them. So let's take an HVAC domain, an HVAC problem. So I can in Riddle define types, the general type of whatever I have in my problem. I have these variables, the p-bar and the probabilistic variables. They can be constants and they can be states, actions, observations. I can define them all as variables. And I have the probability functions. So I define the next state of each variable by a mathematical function. It's very easy to work with, to describe. And I have this is basically the model. By defining the variables like that, I also know what are the relations within the problem. And of course, I have the reward, which is also a function of all the variables in the problem. So let's take an example. I have this problem definition. This is fully lifted. I didn't tell you how many zones you have, how many rooms that you need to hit. You just know that you have something that's called zone. You don't know how many of them. You know that the temperature in the zone is a function of the previous temperature and maybe other zones if there exist and stuff like that, but you don't know anything else. It's not a specific law, it's just a general description. This is the lifted description. Then I can do an instance, and in the instance I decided to instantiate only one zone. So it's only there alone with one heater, and that's it. That's the problem. I have current temperature, this is the state, and I have the next state, it's a function of the current state and the action. Very easy, very to understand. I can use a reinforcement learning engine on that. It will learn, it will do a lot of things. It will probably learn a very good policy. We can argue how much scalable it is, and let's see if we can think out of other instances if it will scale to. So the next instance will be an instance with 3 rooms. We can see here on the side, this is the DBN of the problem. I'm just trying that so we'll see what's going on inside. So we have these 3 rooms, the same single heater, and we can argue that the agent that learns on the single room will be able to generalize for the 3 rooms because it's kind of similar. It's basically the same dynamics. You have this action. The rooms are changing the temperature. Okay, we can believe it will work, but then I can put the rooms to make them adjacent. It's basically the same room. I just changed 2 parameters in the problem. I said room 1 is adjacent to room 2, and room 2 is adjacent to room 3. Now I see the relations are a lot more complicated within the problem. Temperature of zone 2 is a function of all the other temperatures. Room 3 is only a function of room 2 and 3. So the problem is different. Will the agent that learned on the single room or even on the 3 rooms before will be able to generalize and do well on this room? That's a very good question. I'm not sure of that. And I can make it even more complicated, or maybe not more complicated. For us humans, it's exactly the same problem. But now I have these 3 rooms, but I tell you, I'm in the state, I have another room. It's unconnected to anything. It doesn't have a heater. It doesn't have anything. I know from the problem that it's completely disconnected, but it's in the state space. It will change. My agent will see that. It will not or will know how to distinguish that it's an irrelevant part of the state. If it will know how to distinguish it, it will neglect it completely. That's what we hope for. But at least during the training, it will not know how to do that, and it will take a lot more training. The space is bigger. Instead of 3 state space, we have state variables. We have 4 state variables, which for us humans, without doing anything, we know, okay, let's ignore it. The learning agent does not know how to ignore that before it starts doing anything. It has a blindfold. It doesn't know what's going on inside. Okay, so what we did, we came up with, we call it pyRDDLGym. It's a software framework that takes riddle description, domains, and instances, and gives you automatically a gym environment. What you have is a way to interact with a standard gym interface, action states. You observe what the environment wants to give you, and you can apply an action. You can know that it came from a riddle description. You can ignore it completely. You can use reinforcement learning, and you can do whatever you want. On the other hand, you can use the riddle description. It's fully available, and you can know the relations inside the problems are this and this, and you can know, okay, let's try to dissect the problem and do a multi-agent based on the inner structure. Let's ignore part of the problem. Let's do whatever you want. You can do planning ahead because you have the model. You can do whatever you want. You have both the model and the standard gym interface all in one. So this is something that we released quite recently. It works and it's tested now, and we're going to do exciting things with it. I will talk about in the next slide. So what just to recapture what it gives you, you can, from a development perspective, it gives you the way to use to create new environment, new problems, like instantaneously. Basically, you just need to describe the riddle description. You can verify the riddle description. You can do a lot of things with it, and automatically you get the environment. You don't need to hard code the Python environment. You don't need to invest all this time and then look for bugs. And then if you want to do something, go and do a reverse engineering to the code. You have everything in this textual description, which is very fast to develop it and very easy to verify and make sure that it's doing exactly what you wanted. You can do it within pyRDDLGym. You can do it externally. This is completely general. You can do reasoning with the model. You can do a look ahead. We also incorporated a way to visualize domains, some common interface that everybody can write their own visualizers to the domain. You can just interact without visualization. You can write your own classes with a standard interface. So it gives you a lot of power from planning, learning, and development perspective. We also added two, well, so we added more than two, but this is the two interesting tools. So one tool is a visualizer for the DBN. You can extract the DBN of the problem directly from the environment. pyRDDLGym give you that automatically. So this is a UAV domain. So you can see we have these velocities, positions of the UAV. So we have everything. Green and squares are the actions. So these are the three actions. And you see how everything is connected. You see if you want to analyze something, let's say the velocity. So the velocity of the agent is connected only to the previous velocity, and the acceleration it's not dependent of anything else. So this is the DBN on, and it also gives you the XADD, so the algebraic decision diagram, the extended version with continuous variables. So you have you see this is the explicit function in a tree view of how the next state of the velocity is going to change based on the velocity, current velocity, and the acceleration. So there's a lot of algorithms that actually use XADDs directly. SPAD, versus if it's partially observed. The probabilistic planning community did a lot of work on developing these tools. But the learning community does, as far as I'm aware, does not use them. It's like lost in time. But I hope that now that you have everything under the same umbrella, people will start to use these tools within the learning solutions. So now we have this framework. So the next thing we are going to do, and this is something that we started to work on, is to work on a benchmark of home for all things RDDL. So we have these domains, we have problems from past and the present. I will talk about it at the end. IPPC, the International Probabilistic Planning Competition. We're focusing on probabilistic planning and reinforcement learning. So we have a lot of problems. Previous competitions dealt mainly with discrete and Boolean problems, mainly from the operation research community. It was a lot easier. It's discrete problems. So we have a huge archive of these problems. For this competition, I will talk about it. We came up with more problems, most of them continuous or hybrid with continuous and discrete states, control problems, robotics, large network problems. I will speak about one of them. So we're aiming to build a unified archive with benchmarks for planning and learning. So we're collecting now, and we'll continue to do that in the near future, properties and interest from the community of what a benchmark for decision-making, how it should look like for robotics, for continuous decision-making, discrete decision-making, what are the interesting properties, what are the problems that we want to work on, what the properties they exhibit, because currently we're working a lot about Majuko. Everybody in the robotics community know that. Maybe there's a lot of other problems, but I don't know about a benchmark, verified benchmark, trying to capture different properties across different domains to be a single point of work for all of these things. So, okay. So this is just a I don't know, short and very small view of what we did. So we didn't riddle these classical control problems that we have in the OpenAI gym, obviously. We have discrete elevator problems. This is a recommendation system. It's not very visual. Maybe it's hard to see, but there's a lot of points here. So it's customers and providers, navigation problems, UAVs. This is a smart build problem. This is some decision-making, discrete decision-making problem. So this is only a partial view of what we did. This is visualizers. We have other problems with visualizers, which I'll show at least one of them in a second. So the idea is to have a benchmark for all these decision-making problems and hopefully make them pretty as well, so people will want to work on them. And let's talk about a solution, one of the solutions that we're proposing. So this is built on previous work done in our group for deterministic problems, for non-deterministic problems. And the idea is to use backprop as planning. So what does it mean? We have the model, we have everything. We can do a simulation of the states, rewards, action of what's going on in a specific problem. It's a general problem. We have the state, we have the rewards, we have the total return. This is for, and I'm emphasizing that it's for continuous state and action MDPs. So once we have that, we can take gradient of that, assuming we have a way to do that, and train the actions here, a model that solves the actions to as a plan for this domain. So you can simulate rollouts of the problem, take the gradients, train it, and you have a plan. So this is training by backpropagation. Previous work in our group did it on the TensorFlow. TensorFlow has been changed from then to a new version. So we decided to put that as part of pyRDDLGym. You can switch the backend of pyRDDLGym from the regular backend to a backend of JAX that can do symbolic gradients, and you can get the gradients of the problem, and then you can train your policy. And something else you can do with that, you can simulate rollouts, not to the end of the problem, to the horizon of the MDP, but you can take, I don't know, 10, 20 steps ahead and do a replanning every step. So I guess it sounds familiar. It's a rolling horizon algorithm. You simulate forward, you take the gradient, you train it, you take the first action, you apply it, and do it all over again. I'm sure it sounds familiar because it's exactly MPC, but we're doing MPC with backpropagation, and we can do it for linear problems with quadratic costs, like we do in regular MPC, but we can also do it for general factored MDPs or non-factored MDPs with nonlinear dynamics, and we can do it and get interesting results. We get good results when we use that specific tool of pre-planning of this.
Sorry, Ayal, can I ask a question?
Of course.
Are you optimizing over both discrete and continuous actions, or just continuous actions here?
So that's an excellent question, because it leads me to the next slide. So not all problems are continuous. If you want to take gradients, you need the problem to be continuous. And if it's a discrete problem, how do you take the gradients? So fuzzy logic to the rescue. So when we have that, we can, the framework can automatically switch, and you can overload the operators if you want. We give an interface for that if you want to do something else. So when you have discrete operations in your dynamics, we use this T-norm fuzzy logic to replace them with continuous operations. So not everything can be replaced for that. So like Bernoulli or something like that, distribution cannot be replaced like that. So there is a Gamble softness trick that you can use, and we are doing that. But basically what we're doing, we're taking the discrete operations that we have in the model, and we are making them continuous, and then we take the gradients. And as long as it's satisfy a bunch of rules, it works very well. When we're trying to, when things are inherently discrete and cannot be easily be continuous, then it's an approximation, and then it works. But of course, you can find cases then that it does not find the optimal results, or not even suboptimal. We know that. So yeah, so excellent question. We need the problem to be continuous to use gradient-based methods, and we do that within the framework, and we also allow for an API, external API, for if someone wants to replace a specific operation that he is doing in his domain with user-defined operation for that. So this is very good for robotic applications. So I guess most of user control applications are continuous. There's some work that is not continuous, obviously. There's a lot of, maybe not a lot of, but there is work on hybrid NPCs and stuff like that. Alberto Benpora did a lot of work on that, I know, and Borelli, and there's a lot of work going in those areas. But we're trying to put everything under the same umbrella, and we have nice results for that also. And for the last thing, the thing before the last, actually, I'm going to talk about a specific use case. So what we want to do in this case is we want to work on a large model of traffic. So it can be traffic, it can be a smart grid, it can be a multi-reservoir control problem. So I'm talking about network problems, okay, big network problems. And the one we took is traffic, because it's super interesting, and intelligent transportation now is on the rise. And we have this traffic, we have intersections, there's a lot of cars coming, going. Basically, we want to minimize the delay. It can be also a network of packets, whatever you want. We want to minimize the delay, the time that a car is moving from its origin to its destination. The states, usually in these cases, are the number of cars and the queues in the problem. What you can do, you can change the lights in the intersections. Basically, you control the routing. And the dynamics is the basic dynamics of the network. So I will say a word here. There are a few models, acceptable models in traffic. So there are macro models, micro models, meso models. I'm going to talk about a macro model, something that we can actually describe in riddle, not in vehicle-vehicle interaction. So it's going to be a macro model, a flow model. And usually when we work on problems like that, we can identify a lot of interesting structure within the problem. It's not just a flat problem. That's why it's interesting. We have a lot of structure. We have adjacent intersections. We have intersections that are far away from each other, and they are not changing the state, at least not in the next few steps. We can do multi-agents because we know how each intersection is connected to the others. We can use a lot of the knowledge, which we're doing usually in these works. We're doing it by hand. It's like we have an expert that knows, this is a traffic, we have this intersection. We're not extracting these properties automatically yet. So we can, but we should be able to do that for general problems and not just for traffic or something that we know. So we have all these relations, and usually we use simulation environments like Aimstam, Sumo, CD4. There's a bunch of them out there. They are very efficient, very good. But if you want to get the exact model and do planning on it, I don't know how many of them gives you that. It's a close environment, so you can get observation. It does a lot of things, estimation of things in the background, but it doesn't give you the explicit model. You cannot do interesting things about it. So the obvious thing to do is to take these models, the Qt and BLX, these are the known models, acceptable models for traffic, and to decode them in riddle. So we did that, a lot of fun, because it's actually a complicated model. But now that we have the model, and it's not very complicated if you think about it, because you're not doing that for every intersection in the network, you're doing that only for one intersection. You're defining only the operator that tells you how networks are related to each other. Then you can instantiate a single intersection, isolated one, 2, 3, 5 by 5, whatever you want. Just an instance that tells you what is the current topology of the network. So the first thing we did is trying to do a model-free learning. That's the obvious approach. So we came up with an architecture. We call it e-Merlin. It's a multi-agent distributed approach. Each intersection has its own network, but it doesn't see the direct observations of its neighbors, only the one-hop neighbors, but it does see some processed information from the neighbors. So it sees what you see here is you see like it's like an encoded decoder structure. You see the embedding of this encoder. So the decision-making layer is getting the local embedding and the ones from the neighbors. And during learning, it updates only the local branch. It doesn't affect the neighbors. So each intersection is in charge of training its own controller, but we do get some fixed length encoding of what's going on, learned information of what's going on in the neighbors. And we use DQN to do that. And apparently we got excellent results.
Yeah. If you allow a question, what was the motivation for using like intersection specific networks versus, I don't know, some sort of, you could even use a graph neural network or even a regular network with just intersection specific embeddings. But as I understand you, each intersection in your case has even its own weights, not just not just separate embedding.
So again, excellent questions. I like questions that the next slide answers. Okay, so we did that and compared to Presslight. Presslight is exactly a graph neural network algorithm. The problem of centralized versus decentralized, I think they're obvious. So centralized algorithms have all the information, but when the network is, when you have a network of 3 intersections, 5 intersections, you don't care, it's not too much information. But if you have a 10 by 10 network, so you have 100 intersections, that's a huge state space, a huge action space. Even if you have all that information, these algorithms do not scale. They do not know how to find a good policy for that. So
I guess my point is not so much about the state space size. I guess I wonder, is it possible to keep the state space small while still sharing the network weights?
So this is basically what we try to do. We try to look only on local states, because if you look at the whole MDP, you have all the, and it's growing as the network is growing. So this is exactly what we wanted. We wanted to keep the state space always the same size, the size of the local intersection. But you know that there are dependencies between intersections. This is why we had to propagate this information from the neighbors, and we decided not to use more than one adjacent neighbor. We can do that also for the second hop neighbor, obviously. So the idea is to have a constant state space size, even for large networks. So this was exactly the motivation. We didn't want to have big state space and action spaces. Exactly that. This is what we came up with. I guess there are other ways to do it also.
Sorry, can you turn to the previous slides?
Of course.
So here on at the right hand side, you have 3 intersections and 3 stop networks, right? And you are only, seems that you're only updating the gradient to one of them, but like for this one network and the 2 adjacent networks, are they sharing the weights or they don't?
So they're not sharing the weights. You can look at it like a one network across 3 intersections, and you can look about it as one network on each intersection, that it's only this part, the middle part. So this line, these arrows are the communication signals. So this is communicated over the network. Okay. So you can say this is not part of the network. Here I can put lines here and say, okay, this is part of a different network, and you can, but in the forward path takes that into account. So you don't really care if it's propagated over the network or you have a direct connection. Okay. So it is part of the decision making, but it's not part of the training it is part of the training for, I guess, for this part, but it's not for this part.
I see. Okay. So the network will always taking the current intersection and the 2 adjacent intersections, the signals from. But for updating, you only update the branches that is related to the current intersection.
Yeah, so it's 2 intersections if you have 3, if they're on the line, but if you have like like a closed or something, then it will be 4. Yeah.
Right. I see. Yeah, makes sense.
Yeah. But we still wanted to have like, because you can update, you can set the state of these parts to be huge. You can look at states, you can look at the phase, you can, the queues of each lane, what happens in previous time steps, what is the current phase. I don't know. You can always inflate the state here. But we always propagate the same fixed length vector across the network. So even if you take different things here, the communication signal is going to be the same one. So this is also a way to limit, to make it not grow too much, at least not on the communication part, and try to decode all the information in a single vector. Okay, so this is also a way to try to cope with the inflation problem of the state. Okay.
Yep, got it. Yes, thanks.
Okay, so that's a slide for short results. So we did it for grid networks, and we did it also for this specific network. This is the North York corridor. It's on Young and Steele fields, and what we see here, we see 5 intersections that are being controlled by our algorithms, and 3 intersections that are being controlled by the CD plan. They are not playing together with the other intersection. They are not communicating with them. They are not very nice. But that's what you're going to have. You're going to have, at least at the beginning, you're going to have heterogeneous networks like that. So the information flows only on this corridor, and you see all these algorithms. So city plan is the current, and I will call it naive algorithm. I don't know what is currently being implemented in traffic intersections. PressLight is the graphical neural network, the one that is the centralized approach. IDQN and variants of it, just DQN without communication. Deep Marlin is I think it was the state of the art until now. It's a very complicated algorithm. Basically, it learns the observations of the neighbors. It also estimates for each neighbor what its policy. So it has a huge state space. It trains like 2 networks, different networks for each neighbor. So it's a very complicated and heavy algorithm, but it gave good results. So I just show here the training plot of the TD loss. So it's, I don't know, it's a measure of the stability of how fast and stable the learning is. So in red, it's our algorithm. It's pretty fast and very stable because we have a very lightweight approach, and all the other approaches are way more, takes way more time. They have, the error is larger, and even Deep Merlin, which is pretty good, but it's still growing, it's less stable. So the idea is to show that the lightweight approach is fast and stable. So I also believe in simple solutions. If it's too complicated, then there are more things that can go wrong. So that's the idea here. And we see that the algorithm knows how to balance between intersections and to get the total best performance across the whole network. And apparently this scenario where only part of it is controlled and part of it is not, this is apparently a hard scenario. Even for a small network with only 5 intersections, apparently it's a hard scenario. It was way more harder than 15 intersections on a grid or something like that. Just interesting observation. So I will finish now with, I have another slide. So because we have the model, and we have explicitly the model, what we can do now, we can do planning with it. So, and we're actually doing that. We are doing MCPS with the BLX model, and you can have, we can use the reader and pyRDDLGym for that. You can use any other infrastructure that you use, but you need to have the model. So we're doing MCPS. The next step we're going to use the BackProp Planner, which we didn't, everything is kind of new. I didn't say it, I'm here in Toronto since July, so all the results are new. Some of them are published, some of them are in production. So we're going to do next the BackProp planning. and to see how it works, because you have access to the model, and you can do that. There are a lot of interesting questions now that rise from this idea, how to propagate information across the network when you do this model-based planning, because in MCPS, you need a simulation to do the rollouts. You don't have the neighbors intersections. You don't have the information coming from all across the network. So how do you do that? So there are interesting things that you can ask here. How do you leverage what you do know of the model, maybe part of it, and simulate only part of it? So these are questions we're trying to answer these days. So this is current work. And I'm going to finish with the planning competition. So all this is motivated, and we hope to bring the world out to the world of what we're doing. And we're trying to use the international planning competition to encourage people to work on model-based approaches and model-free approaches, not only on one of them, but together. Maybe if you can find a unified way for solutions to solve these problems, we will not have learning algorithms of trying to learn with a blindfold what's going on inside and try to guess what's going on. And maybe we will be able to solve many other problems. We will be able to learn fundamental properties and transfer them. We can many things if you leverage the model we can do. The sub goal of the competition is to set a benchmark for decision-making problems that are interesting for the community. They can be of all across domains: robotics, discrete planning, operation research, classical control. There are a lot of problems. They all fall under the name of decision-making, but each one of them has different properties, and we want to identify these properties and have these benchmarks so people will be able to evaluate their solution and hopefully general solution for these problems. This is being organized by me and Professor Stochastic. The properties, this is what I started with. The properties we are interested in: continuous and hybrid spaces. We have state noise, action noise, everything together. Like, think of, you have a reservoir control problem with multi-reservoirs. You have rain that affect the problem. It's not controlled by you. You cannot do anything with it. It changes the problem, but you have to be able to work with it. You have stochastic action effect. What you do changes the world in a stochastic way, obviously. You have structure. You have a lot of information in the problem. The problem, if you will ignore the structure, if you ignore the rooms in the HVAC problem are adjacent or not, or if there's one room in the state that it's completely unrelated, but you still try to learn with it, you will waste a lot of time, and maybe you will not be able to find a solution. The problems are going to be structured strongly, like every other problem actually in the world. Every problem we solve, we know a structure. Even when I don't know, I make the dishes, I care only about what happens in my sink. I don't care what happens on the stove. Well, I do care, but I don't want the house to burn, but it's not related for my immediate decision making of if to take this plate or the cup. Okay, so everything has structure, everything has relations, inner relations, and it's super important to take them into account. We're going to give a standard GM-like interface with all the assistive tools I discussed. We're going to give the explicit model. People can do whatever they want with it. Obviously, I hope and we hope that they will take everything into account and come up with a super interesting solution for that. The idea is to advance and encourage this research. We are working on that, and we think that's something interesting and worth working on. We have a very nice website. Pretty, that's it. Nothing interesting to say about that. So come and take a look. And that's it. Thank you very much.
Thank you, Ayal, for this wonderful talk. So we will proceed to our QA sections. Audience, if you have any questions, please just unmute yourself and ask here. So probably I can start with one question. I guess so. In the future work, you mentioned about Monte Carlo tree search and like how to leverage part of the model to kind of combine them. Or I'm not sure if I completely understand that. So What do you think of like current model-based IO approach as well? They just learn a model, a word model, and then use that to do simulation, to do rollout, and they can, because the model is learned, it's fully differentiable, they can backpropagate the gradients to update the policy or to help decision making. Is it also a possible solution to this kind of questions?
So there is a previous work. I didn't mention it because I'm not currently working on it, and I don't know if it's active. So we had in the lab, Scott had in the lab a very long line of research dealing with learning models, latent models, and how to plan over them. Okay, so it's super interesting. But when you learn a model, you learn what you see. So you have a model of your observation, and it's also related to OpenRL, I guess, and all other and many other problems. So it's good where you see it. It's not very well good where you don't see it. If you don't have observations, you learn models with errors. You have things that you don't know exactly. So learned models are excellent, but they do have their disadvantages. Okay, I'm not saying don't learn models, and it's not important. It's super important. I think you need to learn models, but what I'm saying is that in a lot of problems, you already have a model. You don't need to tell your agent to learn from scratch without knowing anything. That you have information. You have a lot of information. Why do you try to solve this problem with not one but two hands tied behind your back?
Yeah.
So there are approaches that have a model and they introduce error terms. I know at least one or two works from Stefan Schall about that. So you have a model, you know what's going on. You know the boundaries, and you try to minimize these error terms that everything will work a little better. So you do use a model. So all these ideas are out there. Okay.
Mm-hmm.
So I hope that you can combine everything together. That's the idea.
Yeah, because when you first talk about the environments, like you mentioned 3 examples, right? And I had a feeling that so I don't know, like so I had a feeling like if we really want to learn the model from scratch, we need some I don't know like some causal discovery mechanisms to kind of disentangle the effects of different rooms and different observations. I don't know, different underlying factors. But if we do have some like domain specific knowledge about the like the information of the graph or the model, then yeah, that's much easier, right? And that also makes sense because in many applications we do have those information. Yes.
Maybe sometimes you have abstract models. Okay, so you don't have exactly the interaction, but you have this, the relations, the DBN, you know what depends on what. Use that. With humans, you do that all the time.
Yeah, that's true. Yes.
Can I ask a question?
Yeah.
Ayal, you talked about the JAX BackProp solver for MPC problems, and I'm wondering if it works using collocation methods or shooting methods, or in general, how does it handle compounding dynamics?
Okay, so that depends. So you have a guess of the policy of what you want to do, and you just take the gradients and you try to update it. So you can do a lot of forward rollouts. So this is at least that part is not published yet, and it's still being figured out what is the best way to do that. So there are 2 works that were published in 2017 and 19. They did not do this MPC-like approach. So this is new, and it's still in progress. So there is no specific answer that I would tell you. You do need to do that this way. This is the correct way to do that. This is still in research. Yeah.
Got it. But are you guys trying to handle vanishing gradients or not very much?
So we're not trying to handle vanishing gradients directly unless we're going to find this problem. And we don't see that problem too much in our setting. We don't use that deep networks, so that's not a problem. And I will say that doing this rollout, this replanning for a not too long horizon in the future yields way better results than trying to plan to the end. So planning to the end gives you inferior results by far. Okay, so I guess we're doing that implicitly, but we're not trying to add like these specific components that try to, at least not now.
Got it. Thank you.
Any other questions? So I guess if we don't have other questions, we can stop here. And let's thanks Ayal again for this wonderful talk. And yeah, I'll stop the